microphone, that's right. I don't have a voice, it's already gone. But, excuse me. Well, Jim's absolutely right. You know, this, at my age, the only things that are worth doing are things that are really cool. And DIY audio is right up there at the top of the list. I have numerous projects and things to talk about here today, so we can just start running right through it. Some of you have participated in the Zenductor 2 amp camp. Some of you haven't, so first thing I want to do though is talk about that. For those of you who haven't seen it, there it is. It's a nice little 4.5 by 5.5 inch board with a couple of heat sinks and a transformer sitting right in the middle. It doesn't cost much to build. It's easy to build. It fires right up. The main thing about it is it sounds terrific. I was actually almost shocked when we finally got it hooked up to a pair of speakers and took a listen to it. Because you look at the curves and the specs and so on, and you develop some expectations and you go, well, you know, this is going to be okay. It doesn't cost any real money. You know, and it measures reasonably good, and it's simple enough, and this is going to fill the bill, and I hope it works out. I got it hooked up to a pair of tough speakers, and I went, holy shit, this is really good. And I think that those of you who have already built it or have had a chance to hear it since the build are probably going to, you know, agree with that. I think these are particularly a little more level-headed than I want. Okay. I think there's going to be a lot of agreement. It's actually fairly spectacular, and compared to the previous edition, I think that it makes a big difference in terms of what we get. It's a different actual design. It's in spite of the fact that it has. Oh, can I have the next slide? Yeah. In spite of the fact that it also has an inductor like the first version, in fact, the same inductor, and in some ways much the same layout. We did several things. The most important is we operated the transistors, the power transistors that drive the inductor, as common drain. That is to say, they're strictly followers. The previous edition, we made a single MOSFET do the double job of having both voltage and current gain. And while it worked, it was good for, you know, in my book, it was good for really good at 3 watts, and kind of fell apart and slowly above that. But common source as a follower has a lot more specific job to do, and it's a lot easier, so it can deliver more juice easily without distortion. This one goes to 10, depending on, you know, how high you decide that you want to bias it. So, same inductor. At this time we've got 2 output devices. It's not that 2 output devices in and of itself is the big thing, but we needed 2 heat sinks because we were going to run it hotter. And those of you who built this already know that you don't put your hand on the heat sink for more than a large fraction of a second, depending on how you bias it. And of course, we'll get to that. The voltage gain comes from a little transformer that costs about $7. That is the primary feature about that transistor, because the next step up in the marketplace costs about 5-6 times as much. And so the decision was made, well, let's just go with the little triad single transformer here. And we use it for voltage gain. It's tapped so that a signal comes in. I have these followers. These are just JFET followers running in parallel. The ones down at the bottom here are just a pure common, a current source, very simple. They're not actually doing anything other than providing constant current. The devices above that, those are the array of Q2s. Those are followers. All they do is buffer the input so that whatever you've got for a preamp doesn't have to try to drive the fairly low impedance associated with this little transformer. All the stuff, the stuff up there is for, you know, setting up the voltages and filtering the noise out from the power supply. So we're driving this triad transformer, and we're doing it out of phase on the primary and then in phase at the output, so that the signal driving the output is literally out of absolute phase. The phase has been flipped. The output devices themselves are really happy and deliver a real nice negative phase second harmonic when you run them with the signal out of phase. And their output is also out of phase, and that's why when you get to the output of the device itself, oh, look, this is the negative out for your speaker. Ground is now the positive out. Works like glue, no problems there. Just don't think that you're going to ground the negative output to some other portion of other circuitry that's attached to this. We provided a regulated desktop supply, which is 16 volts at, well, these are rated like 4.5 amps. They're plenty of current. However, some of them have common ground going to the wall outlet, which is something to remember. Some of them don't. We ended up with two different types. They're equally good performance, but one of them has the AC ground running as the negative supply. For that purpose, in case somebody has a problem with that in the system and they're hearing hum, we've provided also some AC adapters that allow you to float that relative to the other grounds that might be in the system. Can I have the next, please? Frequency response, which is this. It is primarily that of that little triad transformer. It's rolling off a decibel at 20 hertz. It's rolling off another decibel at 30 kilohertz. Nothing to know there. Next one. Now, we're going to show you three sets of distortion curves for this piece. The three sets are into 8, 4, and 16 ohm loads, so we get a picture of those. But the important thing is that they are taken at, in this case, 5 different bias points of the idle current that goes through the inductor. And that's the thing that you set with a little potentiometer that's on the board, and you can measure it right across the inductor itself, because it is 9/10 of an ohm reliably. So it is no surprise to see that if you're talking about the bias going from, in this case, I say 1 volt to 1.4, what that really means is 1.1 amp across that 9/10 of an ohm, which is the inductor, to about 1.5 amps. So that just happens to be the setting measured across the inductor. And the current is a little bit higher than that figure. But you can probably guess that the top number with the most distortion is the least bias. In other words, that one there is about 1.1 amps of bias, and you can turn it up, and what you see is that the distortion keeps going down, especially at the higher power levels. And let's see, at 10 watts, it's just cresting 1% distortion. It's a 10-watt amplifier in the 8 ohms. The key here, though, is it's real easy to adjust the bias on this circuit. You can turn it up, you can turn it down, depending on what you prefer for sound or how hot you like your heat sinks. At the 1.4 volt figure, you don't want to have toddlers around the heat sinks on this. They will go, ow, I got hurt, and you don't want that. Next, that was 8 ohms. This is into a 4 ohm load. It's a single-ended circuit. Power does not go up into lower impedances. However, once again, you can see that there's a relative there's a difference associated with various bias points. And in this case, it becomes, a 4, maybe 5 watt amplifier. I have a pair of these running my SR1s at home. The SR1s are 3.8 ohms and 86 dB or so efficiency. They're not easy, they're not problematic loads, but they are low impedance, they're demanding loads. I've got Vincent around here somewhere, he will testify. They sound great with this amplifier. I mean, I was astonished, frankly. And I've left them in. That's what I'm listening to now. But that's with a 4 ohm load, you're really probably going to need that higher bias figure. Can I have the next? 16 ohms, hardly any difference at all. At that point, we're actually running into what are the voltage limitations of a 16-volt power supply. Now, what's interesting about the Zen inductors is that the coil, the inductor, which is kind of like the heart or the big chunk of the output stage, it stores magnetic energy in the iron core of the transformer, and that's sitting there waiting for you to need some minus pull on when the output signal is there. And that's to say, you've got plus 16 to go positive, not quite, you got a little bit less than that, but you're gonna head positive with the signal on the output to approaching 15, 16 volts. But if you let up on that, the inductor will pull it down to minus 15, 16 volts. In other words, it behaves as if there were two power supplies instead of one. Instead of one 16-volt positive, you've got the effect of having a positive and a negative 16 volts. That is a factor of 4 in terms of your output that you can offer to a loudspeaker. And so it ups the efficiency of this quite a bit. And it makes it pretty easy to use a single-ended amplifier with this, but still getting these effects. Next one, please. The distortion versus frequency at 1 watt. Here's where maybe it's not quite so great. Between the triad and the inductor itself, and this is mostly the triad really, you'll find that there's more distortion at the bottom, there's more distortion at the top. And there's just no getting past that with the magnetics unless you spend more money, which is a real function. That's worth noting, because we could have spent, let's see, I guess about 5-6 times more money on the little triad. We would have gotten better numbers here. Interestingly, and this is what I find amazing, is it still sounds good. And I just go, okay, I'm happy. Next one, please. We're on a different subject now. I'll take questions.
On the previous slide, the distortion, is that simple distortion, or is that
I somehow failed to stick a waveform in there. It's a pure second harmonic with negative phase. I mean, but when I say pure, you look at the scope traces and you see, well, what's that sine wave that's right below the sine wave? And you go, that's the distortion. It's almost pure. As you bias up these, there's some limitations here. One of them is what the inductor is worth. It's rated at 2 amps, but at 1.5 amps, you're at the limit where you're going to be able to take it up in terms of you can't go any farther with the bias in the performance, because the inductor starts becoming the dominant distortion mechanism instead of the transistors.
So it's pure negative phase, second harmonic. Do you have any idea of, are there certain frequencies at which a little bit of second harmonic is pleasing or less pleasing?
Well, there it is, less pleasing right now. There's the aspect about second harmonic is mostly, people talk in terms of it being a little warm and such, which is not the thing that I personally relate to. I relate to that there's a different sense of spatial dimension in the imaging. It's as if the venue has expanded and you get literally what you perceive as depth. Not everybody hears that. In other words, but we learned a long time ago that is approximately what most people hear. And the numbers at which they tend to hear that they like is when you're getting into about the 1% region or less. Beyond that, it starts becoming a little more obnoxious. Below that, it's just a lesser effect. But it varies from individuals, and not everybody likes it, and not everybody perceives it as greater depth. Yes?
What about running it off of higher voltages? Like if you've already built a linear supply for the Mini and would like to try that?
Well, first, of course, we need to really run this hotter, I'll tell you.
Yeah.
No, but we've got some physical limitations in terms of with the transistors. Actually, those transistors can handle it. It's the heat sinks that start glowing at some point with higher voltages because the dissipation's there. But the other end of it is you run into the limitations of the inductor too. In other words, it also depends on the load. So this one was fairly optimal. I was afraid to put it, I could have gotten 19 volt supplies and I was afraid to do so. Now, I could do that at home. But even then, I wouldn't let my dogs near it. Part two. The reason I'm going to talk about the Korg triode is that I brought a bunch to give away. And so a certain number of people are going to go, I got this thing, what the hell is it? And so what it is some years ago, a Korg, which is an extremely well-known Japanese audio company. Well, I think we have a picture of it there somewhere. No, we don't.
No.
Oh, okay, we'll go back. Looks like
It's
this.
that.
The article was on DIY audio previously, and the Korg, however, looks like a little computer chip in its own glass. And if you look in there very carefully, you go, what the hell is all that stuff? There are a pair of tubes in there. They're not very powerful tubes. They are strictly there to amplify low-level signals into somewhat higher-level signals, but with a generous dollop of that second harmonic, negative phase second harmonic that I was talking about. They are literally triodes. They're literally triodes that have a really odd way of heating a cathode, but after that they are your classic triode pieces. Interestingly, the mechanism for heating the cathode, which makes it glow blue, is the same that Noritake, who made these for Korg, uses for displays, solid-state displays. In fact, the Past Labs preamps, for years you've seen the little green numbers on the front of the preamps. Those are Noritake displays. Also, interestingly, apparently that all technology is being phased out. However, Korg dealt with Noritake to get these made so that they actually had something that delivered a tube effect for a small game piece that you can buy. It was actually intended for musical instruments, but the amount of effect for generation of, first off, it actually has gain just like a triode, so you can use it for a preamp. But the other thing is it's got a generous dollop of second harmonic. Here it is here. You got a power supply and some filtering and stuff. This is yanked off the article, which is just sitting on DIY audio. You can get the whole thing. There's an input buffer consisting of a FET, and it's not there for any particular purpose than to take care of the fact that there's got a 50K on input pot for the adjustment of level. I didn't want to present the triode with such a high impedance because it draws a little bit of current. Here's the triode, and there's two of them, so this is like two of these guys. It follows a JFET buffer at constant current source, and it's just a follower, and it goes to the output. Real simple, runs on 23 volts. It has an adjustment for the waveform, which is found here's a little 10K pot that you can adjust, and it sets the operating point of the triode, and there's a particular voltage that you want to put it at, and that's in the documentation. Next one, please. Here's the distortion on that. It's a little over 1% at 1 volt. It is, you can always tell a second harmonic, by the way. It's a straight line over the region where you've got pure second, and it follows as the square root of the output. So, for instance here, at 1 volt, it's 1.6 or 7. And you take it down to 1/10 of that, and you look and it is 1/10. Oh, I'm sorry. It's the power ratios are square. The voltage ratios are linear. So you're going 10 to 1 here as you go 10 to 1 there. And we simply adjust it so that it's something on the order of about 1% at 1 volt. But you can turn that up and you can turn that down and you can play with it. Next, please. Oh, there's that sine wave again. Now, this has not had the phase flipped on it. In other words, this is what they do, and in the case of the Korg, there is no additional, the Korg itself being a common cathode operation inverts the phase. Common cathode, like with common source on transistors, is both voltage gain and current gain, and inverts the phase in so doing. If you want your phase to be corrected, you flip it at the speakers, or you flip it electronically before the speakers and after the preamp. So that's one of the things about the Korg that you want to remember. Now you can run it the other way. It'll just sound different. You might like it better. That's a possibility. Different subject now. I wanted to talk about John Hiraga, and in this case, it also relates to that second harmonic. This is the church of second harmonic up here today. but I find this to be an ongoing, continuing, interesting proposition. So Hiraga was of Japanese descent, and he was in France, and he got involved with high-end audio guys, and did a lot of work in terms of developing circuits and analyzing the sound. He became quite famous in Europe, and then very much was a strong influence for the crowd that what we call the Triode Mafia in New York City. And this was a circuit of his. It was called Le Monstre, the Monster, and what it is it's a piece of circuitry that I had independently developed once upon a time, and then I ran across him, and he had done it before. And if you look at some of the stuff that we've done in DIY audio, take the concept, for example, of the F5, which is a real simple circuit, input JFETs and a pair of output MOSFETs, in much the same array, but he managed to get this stuff done with bipolars before a lot of this stuff was, a lot of the MOSFETs were available that were worth anything. Input JFETs, or the input system, he cascoded them. How nice. That lowers the distortion. And in my case, I usually find that they're unnecessary. It's an actual part that you can get rid of. But he liked it. And then what is the equivalent of a P-channel MOSFET up there and an N-channel MOSFET down there? If you were to make those changes, you'd have an F5. Very simple circuit. The main thing about Hiraga was not that he was a big fiend about second harmonic as such. He was very much intent on having his distortion harmonics decline in a particular pattern. You've got, take for example, 1% second harmonic, and then when you hit the third, maybe you're at a 0.5% or 0.75%, and then the fourth is down a little more and down a little more, so that you have this declining staircase of amplitudes associated with the order of the second harmonics. And this guy is still alive, is an unbelievably sharp listener, and I am not the most sharp listener. I had a business partner who was probably one of the best on the planet, and that has propelled my career tremendously, because I had somebody who could render an opinion that I could take as gospel. His name was Joe Sammet, and he's no longer with us. Next one, please. Here's John Hiraga, though. This was, I stole this out of 6 Moons and did a write-up on him. Here he is listening to something. The best part, he's listening to one of mine. Next, please. Now, kind of off the subject of Hiraga, but going back even further, we have a guy whose last name was Schade, S-C-H-A-D-E. I forgot, it's O-E were his first initials, and I forgot what his name was. He was the guy who said, you know, you take a MOSFET, here's the characteristic curves of a MOSFET, and they've got this straight line thing that's going for them. And it's a classic FET scenario. However, if you take and give it a little bit of feedback like this, where you take a resistor off the drain back to the gate and drive it, you get a different set of curves. And those curves look like trilobite tubes. It's the dumbest, cheapest trick you can perform on a gain stage to render the sound that will give you that kind of tube characteristic, negative phase, second harmonic. Next, please. Now,
I've been having trouble.
there was another Japanese gentleman, and this is apropos of, in this case, SITs, S-I-T, static induction transistors, which unfortunately are in extremely low supply after everybody scarfed up the remaining Sony VPETs, and after I scarfed up the remaining token power SITs. You can still get a hold of them, and they're worth having, because it's like having a tube that can do, I don't know, 400 or 500 volts at 30 amps or more at 400 and 500 watt numbers. They even have 1 kilowatt parts that were made by Token. Unfortunately, Token was wiped out by the Fukushima earthquake, and it was not Panasonic. I think it was their parent company by then elected not to pursue that market because there's lots of other hot technologies that were beckoning. The interesting thing here is it was invented by a Japanese guy named Nishizawa, who died just recently. He was, I would say it, if nobody else does, a national treasure for Japan. This was probably, I think as I recall, this is a US patent in 1974, but as I recall, he invented this in the late 40s. And by the way, that it preceded bipolar transistors, preceded all the other transistors that you think about. When he invented it, unfortunately, the processes did not exist to actually make them. And later on, when semiconductor processes started becoming real things, and more research was done, they were able to do that. Now, this is also true of the couple of guys who invented the JPEG, one of which was Oscar Heil. Long before you could build them, and I think the other guy was named Lilienfeld, if I'm not. Sometimes my memory is not the best. But the point here is that these things were invented years before they could be made, because the processes didn't exist. And now I knew Oscar Heil personally because I worked at ESS, and I was working with Heil loudspeaker development, and those were good times. Next, please. So Nishizawa did not just invent that. You've all heard about the latest in Class D amplification.
Yep.
Gallium nitride.
Yep. Yep.
Oh, look, Nishizawa, 1984. Now, you can bet that he invented it about 10 years before that, because it took them a long time to get a US patent on something this important. Actually, I don't know when it was. Oh, well, let's see. It was filed 82. Well, faster than I thought. By then, they probably figured it was Nishizawa, give him a patent. Gallium nitride. I mention this because I haven't heard his name bandied about with regards to, what is now the fabulous hot technology. But there he is. I mention this just so we all give credit to our Japanese friends who invented so much good stuff, which is really useful for hi-fi, one way or the other. Next, please. Well, we've been here before. The Beast with 1,000 J-pets. My daughter painted this for me. It's on the wall in my room. It's named after a Roger Corman movie. Now, Stanley Kubrick and Roger Corman are probably my two favorite directors, producers. There's plenty of other wonderful ones, but they're just the ones who got me the most. This is what the circuit board looks like up close when you're looking at an array of, in this case, 500 JFETs in rows and columns. This amplifier is amazing. Now it's just an output stage, so you have to drive it with whatever you've got for voltage. But it does 30 watts into 8. It does, I don't know, just about 60 into 4. I mean, it's got a lot of heft to it. It is incredible. This is the piece that gets us down into the really, really low numbers of distortion and the really, really high bandwidth, the really, really high damping factors. It's the best of breed. The only problem is each channel uses 1,000 of these JFETs. If you look at the numbers, there are 2 SK170s and 2 SJ74s. You know what it costs to build one of these if you Google the price of those parts. Next, please. Oh, there's the real beast. Okay, I'm just strolling down memory lane here, just in case, I'm just enjoying some of the older stuff. That's it right there. Currently, still running, does a wonderful job. I trot it out now and again just as a crowd pleaser. Next, please. Later on, in fact, about 2 years ago, I built a smaller one, and the intent on this was, well, we can do this over again, and maybe it'll be an overgrown headphone amp, or maybe it'll just drive some normal speakers. It doesn't have to be so powerful, etc. In this case, however, I did something a little different. First off, I used fewer JFETs, but I also used cheap JFETs. And these, I think the cost on these at the moment compared to what you pay for the ones, the J74s and the 170s are, yeah, it's 100-to-1 ratio. So you can afford to build this. And it worked quite well. It is, however, not a push-pull design. It is a single-ended Class A. Half the JFETs are run as constant current sources, and the others just simply follow the signal. Kind of like this inductor, except that instead of the big coil, you have another half of the outputs operating as a constant current source. Next, please. Oh, but speaking of this inductor, I couldn't help but resist to build a Zenductor. In fact, this is the Zenductor 2 model on a board with, let's see, 256 JFETs. It's terrific. It's a lot of fun. I did do one thing. I did myself a favor. If you look in the middle, there is a different transformer than the inexpensive Triad that we used for the build camp. It is the very expensive, let's see, I'm trying to remember the name. Well, it may as well be a Jensen, but it's the
Cinemag?
Cinemag, thanks. 73 years old, it takes me a moment. This works great. Those of you who want to be very ambitious can tackle such a thing because there's no magic about it. However, you got to get with it for soldering hundreds of transistors. And not only that, but they've got to be all neatly arranged and lined up. And so, I developed a technique where I could, with the solder that I'm soldering and tacking it here, I then position the FET, and then I take the iron away. If you do that, you can do about one every 4 seconds. It's just zipping down the road. And so I've got the technique down. Let me tell you, it's excellent therapy. I'm seriously, I do that. I'm happy. This is nice.
How much solder smoke is there?
Well, there is, but that's the other thing. First, I'm in a position to vent my space nicely, but I bought commercial vent suckers, those kinds of things. They're a little noisy, but they pull the smoke that way.
Good.
You have to be very tuned into that. You can't breathe that stuff. Well, you're not going to do thousands of them and still keep your health.
Especially in some.
Somewhere, I guess this is under memory lane again. This amplifier is the very first design I did that was mine. It's also, as far as I know, the first non-switching output stage. Now, it wasn't a very good one. If you look at what the trick is here, it looks like a conventional amplifier everywhere, but on this little resistor and diode, what's going on? Well, when one side, like this one, decides it's, let's say the amp's going positive, and this guy's delivering all the current. Well, if that's the case, then there's no problem. The diode's in full conduction there, and there's no issues. Down here, however, normally these guys would be shutting off. Well, instead of having them shut off, I decided it was better if the fast little stupid diode did the shutting off, because there's very little time associated with that event. So if this is going positive and this wants to shut off, at the point where this guy is going positive here, so the diode shuts off, that guy is still drawing current and keeps these guys biased up, so that none of the transistors ever actually turn off. They go into a flatline zone, but they don't go through the transition of literally shutting off and having to be turned on again, because there are delays associated with that. So this was the cute little thing that I did. I actually built this, and it worked. However, it was fair, and I always anticipated the probability that somebody would point out, but the diodes aren't class A. And of course, that's correct. However, this was my first design. And I did this just at the end of my tenure at ESS, but of course I didn't do it for them. Next, please. I did do this successfully, and I got the patent on it. And this was the first of the threshold amplifiers. And when you look at it, what you see is you got the normal bias circuit here with the transistors, but it's double-ended. Okay, but this is simply a voltage generator. Here's your output stage. Okay, this is very conventional stuff. But I connected these pieces here, little voltage drop and or diodes there, and I forward biased them. And in the case of this, as the output current swings positive, you find that this guy, this Q1, the voltage across it, will increase by virtue of the fact that there's a negative voltage being applied to its base by virtue of its connection here to the output. This one was a far more effective non-switching piece. And actually, correctly done, the diodes never fell out of conduction, so there was really class A everywhere. Now this got we got some noise. Well, it's not really class A because it didn't really run hot. You go, okay, yeah, that's I regard it as an improvement. Besides, I got a patent on it. This actually became rather popular in the commercial circles of audio. This was the version brought to you by JVC. Same kind of, a little more elaborate, but the same tricks. Which is we're modulating the bias positive and negative with respect to the output. In other words, as this goes positive with respect to the output, which it will when we're going through these, then this transistor, in the case of Q7, will actually develop more voltage across it, compensating for the loss of voltage on the top half and leaving the negative half in conduction. Next. Oh, now the same idea, not intended to keep the bias up, but to do error correction, was put forth by Malcolm Hoxford, and this is known as Hoxford error correction. This was his particular suggestion for the output state schematic, and we still have kind of the same thing. We have a bias element that's being varied by being adjusted by the difference voltage between the drive on the left and the output on the top. This was used to correct for the errors that occur in the output stage. And in the case of many of the applications for it, got some really fabulous numbers out of conventional amplifiers. And so I have to smile though, because I see the similarities. Next. Oh, we're still strolling down memory lane. This was the initial patent to describe the stasis amplifiers, which I made once upon a time. And the idea with the stasis amplifier, though, is to set up the circuits so that the gain stages experience both constant voltage and relatively constant current. In other words, that's the deal. Why do we want that? Well, because when the voltage across the device changes, its gain figure changes. And when the amount of current going through the device changes, its gain changes. So to the extent that you can minimize or even freeze these elements, you can take the distortion right out, because actually it ends up with, oh, well, the transistor doesn't know it's doing any work at that point. There's another trick that is very common, goes back even farther. One of the reasons that a triode is so popular is that the variation of gain with respect to voltage and the variation with gain with respect to current are at odds with each other in a normal operation. So that at the point where a triode is conducting more current into a load, you will generally see that in fact its voltage from cathode to anode is decreasing. So the voltage decrease in cathode to anode is lowering the gain, but the output gain is going up because it's a function of current, and they're both logarithmic, and they also, two of these square law functions will literally cancel mathematically. You can take two square law equations and render a no change situation. Now, that's the ideal case. But one of the reasons that triodes are so beloved, at least by me, is you can play that game. You can adjust the parameters of loading and bias, and you can generate positive phase second harmonic. You can go the other way into what we think of as the middle zone and null those out. And you can go further, and now you got a negative phase second harmonic. You can play with them, and it's lovely stuff. That's what was going on here. We were simply playing with the relative levels of voltage and current to the devices and trying to, as much as possible, null the distortion altogether. Oh, another patent. This one's cute, the optical bias. You're familiar with the output stages. You got to come up with a bias voltage to bias them up into conduction so that they're linear. And the voltage source is located here, whatever it happens to be. Most of the time it's a little transistor with potentiometer attached to it. This one's cute because it's got an opto-isolator, which could be sensing off of here, or for that matter, it could be sensing out here. You get a choice, doesn't matter. It conducts when the current goes up. That lowers the bias level. So you plug this amplifier in and you need no adjustment at all, and it varies because the conduction figure for this opto-isolator is extremely consistent. It comes down, I conduct at 1.1 volts, says the opto-isolator, when I'm being driven by something, and the bias will lock in on that, and it doesn't go anywhere, which is very nice. No adjustments, never wanders. Got a patent on that. Next. Oh, who remembers, or if at all, the black hole, which is the device? Okay, you remember the Roadrunner and Coyote cartoons? The Roadrunner there'd be a hole in the ground. The Roadrunner would scoop it up and place it over here and make the Coyote accidentally run through it. And then he can roll it up and put it in his pocket. That's what that was. We were looking for something that did that acoustically. You've got acoustics in a room are a problem, what do you want? You want something that will absorb sound. In fact, you maybe selectively, or being able to move it over to this spot or that spot. And there are such things that, passive, where you've got a big padded pillow of some mechanism, and you put it here or you put it there. This was active. It actually was loudspeakers being driven by microphone. The microphone sensed the sound, sent the signal to the microphone to be in the opposite phase, and made the sound go away, at least locally. So it was equivalent to like cutting a hole in the room. If you put it in the corner, it was like truncating, acoustically truncating the corner. It was really cool. Well, what can I say? We sold some, but it was one of those things that probably before its time. Yeah.
There's actually a company that sells the active bass trap based on that.
Yeah.
Pardon me?
Active bass trap.
Yes.
There's a company that sells those these days.
Patent's expired.
Yeah.
Who are they now?
You can look back and find out who it is.
No, actually, it was really cool. But
It has to be stable though.
Oh,
Because
yeah.
it's a feedback system.
no, it was the most thing you don't want to be too aggressive with your feedback on that. It'll be okay. Next. Oh, this is one of my better ones. The idea here you got an output stage that's been cascoded. In other words, these are the outputs. These are cascodes that normally share some of the dissipation without getting in the way particularly. You can, if you were to take, it's got positive and negative supplies. It's a conventional amplifier. It is cascoded so that there's a series output stage. You put a voltage or current source, in this case current source, as seen there, going from the minus to the plus. And let's say, for instance, it's shoving 1 amp up and into this part of the circuit here. If the output stage is biased at some amperage number, let's say it's biased at 2 amps, and it's a Class A circuit, so it's running hot. One way you take some of the dissipation off that, by the way, is having those series output transistors top and bottom. But the current source allows you to run current through the output stage that has basically nothing to do with the output per se. It simply biases the current up. It biases the transistors up. This got used, by the way, by some other company, I can't remember the name, but it actually saw the marketplace. Not by me. The main thing here was you can greatly increase the efficiency of if you play this game right, you can greatly increase the efficiency of the Class A because the current that is very high is running at low voltage. These 2 points, this point and this point, are decidedly lower voltages than the rails that you're dealing with. So that, you could probably say, well, Class A amplifiers, traditionally they dissipate about twice whatever they're rated at. This could take it down to less than less than a factor of 1. I suppose if you really pushed it, you could take it down by 75%. Actually worked, and actually, like I said, later on, after expiration date of patent, some company decided that they wanted to do that. I don't think they're still marketing today, but it was a clever idea. That may be the end. You got more? Oh no, we haven't got more. The X amplifiers, what we dubbed supersymmetry. This was the first stab at that. Let me see if I remember what's going on with that. You've got inverting amplifier. This, by the way, is the conceptual concept. The real amplifier didn't quite look like this, and these days it's mutated into a whole different direction. But you've got this. These are 2 gain stages. This one actually is a folded. Yeah, this one is actually a folded cascode. it contributes, well, actually, it doesn't contribute all that much. It level shifts the output of these guys. So you've got, but it allows me to create an inverting phase, an inverting phase amplifier. And if you then take and feed the output of this one back into that one, then this one starts mimicking the same distortion on the other side of a balanced circuit. In other words, you're looking at an amplifier where it's differential output, and it's got distortion here, it's got distortion there. But we take the distortion component and we feed it back to the other side, and it cancels. Actually works. Got a patent. I'm still selling variations. My paycheck still comes from mutated variations on this circuit and concept. Let's see, is there any more? Oh yeah, there's still more. I used to get patents. I stopped getting patents a long time ago because I realized that they look good on the wall and that's about it. You know? Or they are good for like standing out here and going, look what I did. But this is the Aleph circuit. And the idea here is you have a, normally a single-ended amplifier would have a power transistor here that is the actual gain stage, and then it would be biased by something, often is not either a resistor or maybe a constant current source. In this case, it is biased by a non-constant current source, and that's this arrangement right here. This is the power transistor that's working. This one develops the bias voltage across it, but it's tapped into the output so that when, for example, the positive, when current going output through R4 is positive to the load, this guy starts being pulled at and generates more drive for this guy so that the bias is no longer constantly coming from the top. It has become a gain stage. And yet the whole thing is, single-ended classical. Looks and behaves a lot like it, but with greater efficiency and also better numbers. I'm not sure, is that the end? Oh, yes, it is the end. I wanted to show you what a proper bench looks like. That's I've seen worse. I mean, well, I had Vincent and Jim Tiemann visit me just before this event, and we were still scraping everything together, making those inductors work and so on. This was neat compared to that, and they will tell you that that's true. Anyways, that's it, folks.
For a few minutes. Does anybody have any questions for Nelson about life, the universe, or anything else?
Nelson, these two amplifiers you're talking about, one using the MOSFETs and the other one using the large number of JFETs. What is your opinion of using MOSFETs, vertical MOSFETs versus JFETs for those kinds of amplifiers?
You work with parts and you develop affection for some and not so much for others. JFETs are my favorites. They just are. And it's hard to, they're the depletion mode, so they bias themselves. They're fast, they're pretty linear, they're very tolerant. You don't zap them like you do a MOSFET with a little bit of spark. It's just got a lot to say. And the other thing is that if you buy 1 million of them, they're 5 cents each. I can testify to that. So, my favorites, of course, are the Toshiba J74 and 2SK 170, and the LSK versions also. But my affection for those is unbounded. However, you look at what they cost. Now, I remember when they were 30 cents. And you could buy a lot of those JPEGs then. Toshiba, I love Toshiba, and one of the reasons I've always loved them, not only do they make the wonderful parts, but they were really, really considerate of the marketplace when they were dealing with discontinuing and stuff like that. Toshiba, a year before they discontinued those JFETs, they said, we're going to discontinue those JFETs. We're not raising the price, not doing nothing. Get your orders in. We're not fooling around. And then, like the month before, we're reminding you, we're not fooling around here. Get your orders in. Well, and by the way, we took, we should have done a lot more, but we bought a big bunch of them. Then it's like, this is D-Day. We're discontinuing them, but we're going to hold it open for another week or two. Get those orders in here. We're not fooling around here. And then eventually they actually did discontinue. I know a gentleman who bought 500,000 of them. I bought somewhat less than that, but remember they were 30 cents back then.
Yeah.
And now, I don't know, on eBay and such, they start at $5.
Wow.
And if they're all matched and stuff, maybe more. So, that's why I like Toshiba. Not only did they make wonderful parts, but they gave you every chance to get in on the action while it was still good. So those are my favorites. That's why I like the Beasts. What is this? I got 1,000 JPEGs. And it sounds terrific. I honestly think that that's the best sounding part.
You could do a surface mount version of that.
Yes, but I think, as I recall, it's only the ends. The other thing is it doesn't dissipate as much energy on the surface mount. And it doesn't look as cool. Let's kid. This is not dialysis here. This is entertainment. So, any other questions?
Nelson, just FYI, for anybody who wants to make a piece using the J113s, they're 12 cents a piece if you buy 100.
That's not bad.
Now, that's a bargain.
That's on semi.
Now, you roughly have to use 4 of those to get the game figures and such. And so you got to buy more of them. But the dissipation numbers go up, so that there's some merit to that.
So,
Yes.
so to that end, will you write that up with a Zenductor game stage and stuff so that you can potentially,
Well, are you going to publish a Zenductor Beast?
yeah.
I just did. I mean, you take the MOSFET out, you put in an array of JFETs, you're done. They're just running in parallel.
So yeah, we'll figure that out when we know. It's just that you're literally going to be buying thousands of the JFETs of the 113s. You might need to match them a little bit. So there's going to be a lot of work involved.
They're still selling them.
But they still make them, exactly. So,
11 cents a piece, you buy 1,000.
yes.
Yes.
Well, effectively. I mean, the newer version of that using the JFETs that don't cost $5 a pop. So,
I saw some J74s from Linear on the Mauser website
Yes.
a couple days ago, listed as new parts.
yeah.
Are you familiar with that? Is that the
Yes. That's what's available commercially equivalent.
And they wanted like $10 a piece for them.
Yeah, how about that?
Okay, so they're moving on those. Okay. I didn't know, because everybody's always looking for replacements.
Well, if you only got a few of them in what is a fairly precious circuit, then it's worthwhile.
Yeah.
You can go on eBay and you can pay less for Toshibas, assuming that they're legit.
Right.
Because one of the sellers on eBay is. Right?
Punky Dog.
Punky Dogs is
Oh, by the way, Punky Dogs,
Yeah.
okay, is a good friend of mine.
Okay.
He's the guy who bought 500,000 of them. I kid you not. Years later, I bought more from him. So, I mean, he's a terrific guy. And you don't know who he
Your
is,
prices are better.
but you don't know who he is probably. But he's actually on the forefront of some incredibly fantastic new technology with regards to DACs. And that's referred to as immersive, is the outfit. And that's just breaking now. But, he's found a way of like incredibly increasing the dynamic range of a D-to-A converter. Questions? Sorry.
Yeah. Could you comment a little bit more on why you initially patented and why you then stopped? I mean, does it
Oh,
not
in the old
help
days,
against
in the old
copying,
days,
or-
having a patent was like, this circuit's good,
Yeah,
look, it's
no,
got
I
a
see
patent.
that. So, yeah.
You know, and also the competition was a lot different back then. I mean, I had think of the number of Japanese companies that came out with non-switching amplifiers within the space of 2 years of me doing that. Virtually all of them. And there was, you know, as a practical matter, there was no point in getting into arguments over that because I didn't have, you know, very much in my pocket then. I don't now, for that matter. But, you know, the whole notion of legal defense against a Japanese company, the whole thing smells bad and is gonna deplete your bank account.
Follow-up question. Did you ever get the feeling that the examiners would actually, I mean, try to figure out whether that circuit actually worked?
Yes.
I mean, so
Yeah,
they do.
they're pretty critical. They're going, well, what the hell is this? You know, this doesn't work. And
But I mean, having a prototype, is that a requirement or?
I did not provide any prototypes. I
Yeah.
simply said, this circuit does what I say, and they go, yeah, guess so.
Just to add to your comment, you know, for patents, you do have to demonstrate reduction of practice, right, to obtain a patent.
You know, I don't know anything about it because I had a nice patent attorney,
Yeah.
great guy.
You have to demonstrate, I mean, I'm in that around 60 patents in biotech, right? And a key attribute or requirement is reduction of practice. You gotta show that it works in the real world, or you don't get a patent.
Oh, well,
It's
in
real
this
simple.
case, it was reasonably obvious.
Yeah, yeah, of course.
You know, oh yeah, I mean, you put the signal in the transistor and it does that, yeah, okay, that's, you know.
It has to work.
I had a great patent attorney too. Oh, the other reason I don't do patents is he retired. And he was terrific, and I didn't even want to go shopping for anybody else. Yes.
Regarding such stuff, obviously if you go on eBay at the moment, there are a lot of amplifiers that are labeled as pass
Yeah.
lamps.
How about
And
that?
they even look like.
And they spell my name right.
What's the laws? What can you do about that, or do you bother?
Well, what, you know, I don't really choose to do anything about it. Everybody who really wants one of my amplifiers has no problem figuring out which ones those are. In the meantime, like I said, they're spelling my name right. I have people who have bought my amplifiers just because they want the real, genuine thing. You know, and so I don't see, the question here is what's my damage, and apparently, no.
I mean, obviously, if it's a $600 amplifier versus a $6,000 amp, you know what's what.
Yeah, you know, the customer is reasonably discerning here, you know, and it's not for me to say whether they particularly, or whether those are really good amplifiers or not, because they don't end up coming, they don't come across my bench.
So
I certainly don't repair them for people, you know.
There's nobody actually for warranty repair on this.
Well, the price is low enough that maybe that's not such an issue. I have not heard anybody go, I bought this and it didn't work. No, it's probably put together by people who are reasonably competent. They're taking slight advantage of the association.
Kind of so long, I mean, before they used to be a little stealth about it, they wouldn't even say the name. But now, I mean, there's other amplifiers.
Well, the word got out that I don't chase them. I think that's probably it, you know.
It's like, there's the guitars now as well, they're called Gibsons. They're basically, there's a lot of them out there.
Gibson probably would chase them.
And they're stabbed, made USA.
But Gibson's a large company, whereas, you know, me, I'm just a little company. And I've got better things to do in my life, honestly. You know? I mean, what I like to do, what I always like to do, is I like to build stuff. When I was a little kid, what did I do? I built stuff. I built some great stuff too. I had a Jacob's ladder that was like from here to like there. You know what a Jacob's ladder is? It's that Anne Frankenstein movie effect. And
So life's too short going after all these guys, right?
I ended up with that because my gas laser didn't work. But I had a 10 kilovolt, it was about a 500 watt transformer left over. So,
And since you gave us a sort of a trip down memory lane, going back, would you start a hi-fi company today, if you could? And if you wanted to do that with what you've learned now, what would be some of the things you would say, do this, don't do that?
oh, that's tough. If you're gonna start a hi-fi company today, and you're not Mr. Mega Millions, then you go for the idiosyncratic top end. I don't advise Class D as a concept because I think it is quickly becoming a commodity market, and the little guy has zero chance of going anywhere unless he's such a genius. But you know, the genius function already seems to have been applied to Class D. So where are you? Well, you can harken back to tubes. There's still a market for that. Doing something unique with tubes at this point, a little tougher. Not that it couldn't happen. I think that there's opportunity, but it's a long road to hoe. I mean, I have been building amplifiers. I've been getting a paycheck from audio for 58 years. No, that's not right. That's not good. I've been building audio for 58 years. I've been getting a paycheck for probably 54 years. So I've just got this momentum thing, and I've got my infrastructure, and I've got the people that I associate with. That all helps me. If you don't have that, you have to recognize that, especially in high-end audio, there's no, this thing conquers the world instantaneously. Or in the old days, back in the 70s and late 60s, you could do this. But I don't recommend it. I mean, if this is what you want to do, then I recommend it. But
Yeah. Fantastic. 58 years. Okay, so Nelson, thank you very much.